Oops. Okay. We are in chapter 10, and I did put the PowerPoint on D2L, so you guys should be able to either print it off or just try to somehow go through it with me, because you still need to be able to do, some of these examples and things like that. So, all right. So chapter 10 is still about energy, but now we're in potential energy. So we kind of talked a little bit about potential energy in the last chapter, but this one gets a little bit more involved. So, all right. Is this where we start on here. Okay. So potential energy has this funny looking symbol, this U, in this book, and it's just saying to consider two particles that are interacting with each other, and to say that it's in a system. Okay. So we could say that a system is really small. Like we could say a system is between, atoms, so like very small atomically. We could say that a system is, the world. We could say that a system is the universe. So it just depends on what we define as the system. And so these particles are in a system, they're interacting, and these forces are doing work on them, okay? And so the potential energy is going to change. And so this is showing you that the change of potential energy, so there might be a change of potential energy, which is negative work. So think about it like, and I think it probably does it over here a little bit, but I've missed a little bit on this page, so I'm going to go back for a second. So we'll look at that picture here in a minute, but then this is also saying that the system's kinetic energy increases if its potential energy decreases. And we'll show sort of like how that works with the total energy. Okay, so think about it like this. If you drop a ball right here and it's this far off the ground, what's going to happen to it? It's going to fall down, right? So if you pick up this ball and pull it against gravity, okay? So then if that's the case, if it's going up, then it's negative work, okay? So work is like going against the gravity. And that's what it's saying here. It's showing that you've got a figure and you've got two balls and they have mass. So, you have to have mass, obviously, to have any kind of potential energy or even kinetic energy. And this is saying, that's for gravitational potential, I guess I should say. And it's going up this vertical position, and we're saying that the ball's system is the ball and the earth, okay? And gravity is included there. And this is showing that this symbol with this delta U, we know is potential energy, but when it has this little subscript G, that means it's gravitational potential energy. So the work, okay, of ball B is the work gravity does on the ball. And the work E is the work gravity does on the earth, okay? So you've got two things happening, the ball and the earth in this situation, in the system, okay? Ball B is the only thing that's happening here, but this is showing you that this is the force of the ball on earth, okay? Because once that ball hits, what's the earth going to then do as far as Newton's third law? It's going to have an equal and opposite reaction, okay? So once this ball hits, there's going to push back at it. All right, so the work of the earth is practically zero, since the earth has almost no displacement, right? In order to have work, you have to have force times distance. And the force of gravity on the ball is just negative mass times gravity, okay? So we can figure out the force if we have the mass by multiplying it by gravity. And so the gravitational potential energy, all right, that's the negative work done, okay, which is saying that it's going, it's the work that's going down, right, which is what gravity is doing, and that's telling you basically the direction. And this is another way of writing potential energy for gravity, is mass times gravity times height. Okay, and this is the change of height because you might have an initial and a final position. Okay, so if that's the case, then you'll have to find the change of that, the difference of that. Okay, so still with gravitational potential energy, and this is sort of your main equation, right? And in order to find, you could have kinetic. I was saying this a couple slides before, that you could find the total energy. So the sum of the kinetic and the potential energy is not changed when an object is in free fall. So basically what it's saying is, let's take for instance that we had this ball right here and we're just holding it for a moment. Does it have any kinetic energy? No. Okay, so that would be like 0. And does it have potential energy? Well, we're holding it up here. Like, let's say this is the ground. Okay, so we're holding it right here. And this is, say, 2 meters high. Okay, so yeah, it absolutely has potential energy. So it does have initial potential energy. Well, let's say we drop it. Okay, let's say we drop it and it's right here. We take a picture of it right here. Does this still have potential energy? Yes, it absolutely does. Why does it still have potential energy? As it's falling, why does it still have potential energy? Because is it still off the ground? It still has a certain height, right? Well, let's say this is like 1.5 meters. So as long as it still has height, it still has a Y value, then it still has potential energy. But does it also have kinetic energy at this point right here when it's moving? Yes, because it's going to have a velocity at that point. So whenever you take this snapshot of this ball right here, you should be able to add up the potential energy and the kinetic energy, and it should equal whatever it was at the beginning, whatever the potential energy was at the beginning. Okay, so, that's just going to depend on the height that it is and the velocity that it is at that point. And you could find that doing different labs if you had pretty cool equipment, if you had some photo gates or even a video that you could calibrate somehow, you could be able to figure out like what the velocity was at that point. So kind of cool. But I do want you guys to kind of, just kind of look at this equation, because this is going to be something that you're going to use a lot, where you're going to have to set up final plus, final kinetic plus final potential is equal to initial kinetic plus initial potential. Okay, and this is stemming from the conservation of energy, meaning that there is no loss of energy in this at all. Okay, so we've got this example that we can do, saying Raphael uses a slingshot to shoot a 25-gram pebble straight up at 17 meters per second. How high does the pebble go? All right, so let's write some information down. First, we're given 25 grams, which is obviously a mass. And do we like grams, by the way? No, we definitely want to get into kilograms, okay? So just kind of keep that in mind, make sure your units are good. So that ends up being 0.025 kilograms. And then it says that it's going straight up at 17 meters per second. So 17 meters per second is the velocity. And so does that mean that it has initial kinetic energy or final kinetic energy? Well, it's just showing that it goes straight up at 17 meters per second, and it wants to know how high it goes. Okay, so if the pebble gets to the very top, I wish you guys could see me right now because I'm moving my hands, but if the pebble goes all the way up to its very highest point, for a split moment there, what's that pebble doing in midair before it starts to come back down? just kind of sitting standstill, right? So at the very top point, at the height of it, what is the velocity? The final velocity right there at that very top point is 0. Okay, so kind of keep that in mind. And this is wanting us to figure out how high it is. All right, so let's write this equation that we just had. So we had final kinetic plus final potential is equal to initial kinetic plus initial potential. Okay, so what does all of that mean? Well, first off, let's get rid of some of this stuff, okay? So, did we have initial kinetic energy? Did we have initial velocity? Yes. Okay, so if that's the case, then let's say that that is having 0 initial kinetic energy. Okay, and then do we have final kinetic energy? Well, at that very highest point, is it moving? No. So we do have final potential energy though. So now we can kind of set these equal to each other. We know that potential energy is mass times gravity times height. We know that kinetic energy is 1/2 mass times velocity squared. And what are we actually solving for? We're solving for height, which is y. Okay? So if we move this stuff over to the other side, those cancel, and then my mass cancels. So do I even really need the mass of this situation? I don't, actually. So you have 1/2 times the velocity squared over gravity. So you've got 1/2 times 17 meters per second squared divided by 9.8 meters per second squared. Whoops, went over to the other page there. So whenever you solve that, you should get 15 meters. And that tells you what the final height was. You know, as it tells you really though, like how high the pebble goes. Okay? Now, could you have another step to this where it starts to go back down and then you have to find other stuff? Absolutely. You know how physics goes. Sometimes you have, to do one step and then you have to go and do another step. That's just the beauty of physics, right? I can kind of see some of your faces right now as I say the beauty of physics. All right, so this is saying to rank in order from largest to smallest the gravitational potential energies of the balls. Okay, so which one has the largest here? Potential energy. So how do we get potential energy? First off, do they all look about the same size? They do, and actually it's the same ball. So, or I guess we could say whatever, but let's just assume they all have the same mass. What's the only thing that's different? Well, the height. Okay, so which one has the largest potential energy? Well, it would have to be 3. So it's either C or D right here. These guys, we can knock them out. And what about the next one? So 2 and 4 are both at the same height. One's going up and one's going down. Does the direction affect the potential energy? No, it's just basically the height. So they're both at the same height, so they're actually equal in this case. And then, of course, number 1 is the lowest, so it has the least amount of potential energy. So our answer there is D. All right. And then this one, let me see here. This one's showing Amber and Carlos use coordinate systems with different origins. So you can have different origins. You can see that Carlos is at 0 meters, or the rock's at 0 meters. And over here, Amber's got the meter stick where the rock's at 1 meter. So this is showing that no matter where the rock is, Amber's value of gravitational potential energy will be equal to Carlos's value plus 9.8 joules. If you are going to do the gravitational potential energy of 1 kilogram times 9.8 times 1 meter, you would get 9.8 joules. If you went over here and you did it for Carlos's value, see his height right here is at 0 meters, so everything becomes 0 then at that point. But it says if the rock moves, both will calculate exactly the same value, This is just an example of the zero of potential energy. It depends on the coordinate system and what you are considering, the 0 point there. And so it should be clear to you on the problem that you're given what the 0 point is. All right. I'm going to stop the video because I feel like I've gone a little bit long, and then I'll